So we're going to be finding the real zeros, and then we're going to build into finding all of the zeros of a higher degree polynomial. So with this stuff, most of you should have done this before in Algebra 2. Actually, all of you should have. Conferred with all the Algebra 2 teachers, and yes, this was covered by everybody. So there should be a lot of review involved here. The first thing we're going to cover really quickly is long division with polynomials. And we'll get it out of the way. You've got to be able to do long division, not necessarily for this section, but when we get into 5.4 and 5.5. So I'm going to review long division, and then we'll swap over to synthetic division, which is more aligned to what we're going to be doing in these two particular sections. So long division is the beginnings of synthetic division. So that's why we show it here. So if we're going to divide x cubed minus 4x squared minus 5 divided by x minus 3. We're going to do that with long division first, and then we'll do it with synthetic division. And make sure we're good to go there. All right, so long division, we're taking our dividend, which is what we're dividing into, and put it in that little symbol there, long division symbol, x cubed minus 4x squared. Then we don't have a term that's a plain x. So when you're doing either long division or synthetic division, if there's a term missing, if you start at x cubed, you've got to have a representative from x cubed, x squared, x to the first power, and x to the 0. So you got to have one of each starting with your highest. If there's not one there, you need to put it in its place. So you can put a 0x in there because that's how many x's there are. There are none of them. And then you put the minus 5. On the outside is going to be your divisor. We're going to divide by x minus 3. Okay. When you're doing long division, you want to look at the leading term, the first term. Okay. So the first term of our divisor, what we're dividing by, is x. And the first term in our dividend is x cubed. So what times x would give me x cubed? X squared. So I'll put that above x squared. Then, what you did long division in elementary school is you multiply, you multiplied and subtracted. So we're going to multiply and subtract, but we're multiplying x squared times this entire x minus 3. So it's like distributive property. X squared times x cubed, x squared times negative 3 is negative 3x squared. And we're subtracting that. Now, x cubed minus x cubed, what happens to them? Goes away, cancels out. And then negative 4x squared minus negative 3x squared. No. Negative x squared, right? Negative 1x squared. Negative 4 minus negative 3. So we get negative 1x squared. And then we bring down the next term. Then we still look at the first piece of what we're dividing by. It's x. What times x would get me this negative x squared? Negative x, right? So negative x up here. I'm going to use a different color. Then we distribute. Negative x times x is negative x squared. That's going to be bad in just a minute. And then negative x times negative 3 would be positive 3x. And again, we're subtracting that. So negative x squared minus a negative x squared, it just cancels those out, what we want to happen. And then 0 minus positive 3x, the negative 3x. And then bring down the minus 5. And then what times the x in front gets me negative 3x? Negative 3. and then distribute again. Subtract. The 3x's cancel. -5 minus 9 be -14. This is our remainder. And the way we write a remainder in polynomial division is we put plus -14 over x minus 3. It's kind of like a mixed number, but it's a polynomial. Is what's going on there. So long division, not incredibly difficult stuff. It's just got a lot of places that you can make mistakes. I mean, you look at how many operations took place here. Well, there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then we had to write it the right way up here. So there's like 17 steps out of that for long division, and that's it lived up to its name, long division. So you got to. There's a lot of places that you can mess up there. There's still a lot of places you can mess up with synthetic division, but it does simplify the process quite a bit because it takes the variables out of the way with synthetic division. So let's review that real quick. Synthetic division. Same problem. We're dividing x cubed minus 4x squared minus 5. We're dividing it by that x minus 3. Same thing that we did in example A, but we're going to do synthetic division. Just to review that. So when you set up synthetic division, this is how I set it up. Make this kind of lazy backwards L laying there, and then I put a little shelf right here. The number that goes on the shelf comes from what you're dividing by, your divisor. And the way you get what goes on the shelf is you say, oh, x minus 3 equals 0. And so that's going to be x equals 3. So 3 is what goes on the shelf here. It's the opposite sign of what's in the factor. It's what the x-intercept would be. If you were thinking about what kind of like what we did on the quiz today. So, and then what your dividend, what you're dividing into, is going to be the coefficients of this polynomial. Coefficients means numbers in front. So 1, -4. Then we've got that missing piece again. We don't have that x squared, so we put a 0 in its place and then a -5. And then synthetic division, it happens a lot faster. It's not long division. It doesn't take quite as long. But there's still a lot of operations that happen. So the first thing you do, every problem with synthetic division, is you drop the leading term down. So you just drop that 1 down here. Then you start your process. It's 1 times 3 is 3. And then in synthetic division, you don't subtract, you add. Okay? What's -4 plus 3? And then you multiply -1 times this 3 out here. It's going to get us the -3 right there. What's 0 plus -3? -3. And then multiply again. -3 times 3. -9. What's -5 plus -9? -14. That right there is your remainder. Just like it was in example A. It's the same problem. It just doesn't have the variables in it. So when you go to write your solution, we'll put the variables back in. Yes, ma'am. Yes, that is correct. The last piece here is always going to be your remainder. Always. And sometimes that's 0, and that's a special case. That's what we're hoping for as we go through here. Tristan? Here's the difference. Long division is needed if you're having to divide by a polynomial that's degree is bigger than 1. That's when you would need to be able to do long division. That comes up some in sections 5.4 and 5.5. When we do those with the rational polynomials, there's some things that we've got to do there. If you're dividing by a linear divisor, your divisor is linear, then synthetic division will work, which is what we're going to do mostly in here in this section. These two sections is linear pieces. So we'll use synthetic division here on out. in these two sections. But long division, if you've got to divide by something that has a degree larger than 1, that's where long division has to be used. You can't do synthetic division with something that's got, if you're dividing by x squared minus 5 or something like that. You can't use a synthetic division. All right. Now, what does that mean as far as a polynomial? Well, anytime you divide a cubic polynomial by a linear polynomial, it's x cubed divided by x, so it reduces the power by 1. So this turns into 1x squared minus 1x minus 3, and then the remainder, we're going to put plus negative 14 over x minus 3. That better be the same answer we got in example A, and it is. Synthetic division always reduces your degree by 1. That's fairly important. That synthetic division always reduces your degree by 1. Now, that remainder, and Kylie asked, is that remainder always the last digit? Yes, that last digit there's always the remainder. When that remainder is 0, then we have something special happening. And that's the factor, and we'll say slash remainder theorem. We're going to combine those two theorems together. X minus, we'll say C, and C is just a number, okay, any number. Okay, X minus C is a factor of a polynomial if and only if f of C equals 0 and the remainder is 0. That's kind of a redundant statement. These two things that are underlined there are the exact same thing. When we do synthetic division is what I call it. You'll read it in textbooks called synthetic substitution because it's exactly the same thing. Synthetic division, synthetic substitution. If you see that, hear that, they are the exact same thing. And what it means is if I plug in this number and I get a 0 as the remainder, that means that that polynomial, it's kind of like when I divide 12 by 4. What's the remainder when I divide 12 divided by 4? The remainder for that is 0, right? What that means is 4 is a factor of 12. If we divide a polynomial by x minus something and we get a remainder of 0, that means that x minus something went into that polynomial evenly. So it's a factor of it. So it's the same idea as with numbers, but it's polynomials that we're dealing with here. So it's a little more complicated in getting it done, but the meaning is still the same. That when the remainder is 0, that means it went into it evenly. So that's what we're banking on happening here, is that sort of thing. So let's look at a couple examples here, or an example of this. Is x minus 1 a factor of f of x equals 2x cubed minus x squared plus 2x minus 3. Okay. We want to know, is this a factor of that bigger polynomial? So x minus 1, is it a factor of 2x cubed minus x squared plus 2x minus 3? And the way that we would decide that is we would do synthetic division. And the reason we can do synthetic here and not long division is, what's x minus 1? It's a degree of 1, so it's linear. So we can use synthetic division. That makes it easier. Everything you're going to do in these two sections is linear. So when we do that, we set up our synthetic division. What goes on the shelf? Positive 1 or negative 1? Positive 1, because it's the change the sign. Now, what's the top row of our synthetic division? Try again. 2. Yeah. Get those coefficients. Make sure if there's a missing piece, you put a 0 in its place. Okay. What do I do now? Bring the 2 down. Times it by 1. So that's 2. And then what? How'd you get that? Add. That's what I'm after there. So that's 1, 1, add 3, 3. What's that remainder? 0. What's that mean about x minus 1? That it is a factor. So so there'd be a yes on this. What that does for us is it takes that polynomial and it factors it as x minus 1. And then this is what's left. 2x squared plus x plus 3. So we've taken a third degree polynomial, or a cubic polynomial, that's a better name, and we factored it a little bit with synthetic division, and now that leaves us a linear factor and then a quadratic factor. When we've got a quadratic factor, we got all kinds of tools for quadratics. We got factoring, we got quadratic formula. Technically, we have complete the square, which nobody ever uses. I feel bad for it, but nobody ever uses it. But we got a lot of tools for getting this to work here. So synthetic division is going to help us break a polynomial down to where we get some quadratic pieces out of that. So let's start actually doing that, breaking polynomials down from nothing. So let's do this. We got we want to find all the possible rational zeros and factor this function f of x equals 2x cubed plus 11x squared minus 7x minus 6. So there's our polynomial. If I'm in an Algebra 1 class, maybe an Algebra 2 class, I would, and so you all have had those classes. So if I ask you what method of factoring could we try on this, you should know the answer to that. Why? Grouping is right. Why? Why is grouping the way to do it? There's 4 terms. If there are 4 terms, grouping is the way you would try. What we run into here is that if I group the first 2 together, the only GCF there is x squared. And if I pulled out a GCF of -1 here, I don't end up with it working. Then it doesn't work. So that's why we need synthetic division and all that, because grouping is wonderful if it works. So that's always an option, but it doesn't always work. So this is where the synthetic division comes in. Now, here's where we've got to make a list. It said the possible rational zeros. Y'all remember doing this P over Q list in Algebra 2? I guarantee you there will be quiz questions that will ask for just the P over Q list. There will be test questions that ask for just the P over Q list. There will be questions on the final that ask for just the P over Q list for a polynomial. Okay? Now, P over Q means the factors of the constant on top. So this is P, this is Q, okay? The constant is on top. So the factors of 6. What are the factors of 6? Okay, so 1, 2, 3, and 6, right? Technically, it's plus or minus on all of those. I'll let you just put a plus or minus in the front. What are the factors of 2? 1 and 2. That's the only things it could be. Now, that's not the list. That's just getting started to start the list. So 1 and 2 are on the bottom. So the first thing I'm going to do is I'm going to divide each of those by 1. And it just gets me that list back that's on the top. So the P over Q list is plus or minus 1, 2, 3, and 6. And then when I go and divide each one of these on the top by the next factor that's on the bottom, what's 1 divided by 2? What's the fraction 1/2? What's 2 divided by 2? 1. We've already got 1 listed, right? So I don't need to put it again. 3 divided by 2. Oh, it's the fraction 3 over 2. 6 divided by 2. I've already got 3 listed, right? So I don't need to list it again. So I've narrowed down, by doing this P over Q list, I've narrowed down the possible zeros for this polynomial from every number in the world to this list of 12 numbers. Positive and negative on each one of them. There's 6 of them, so there's 12 possible rational zeros. That doesn't mean that all of them are. Technically, it doesn't mean any of them are. But it says if they're a rational zero, then it will be in that list. And what that helps us do is narrow down what we need to try in synthetic division. Now, when I was in high school back in the dark ages of the late 90s, we didn't have the nice graphic calculators that you guys have. So we didn't have the luxury of being able to graph the polynomial quickly and look at a graph. We had to just guess at one of these 12 numbers and try it. And if it didn't work, try another one. And if that didn't work, try another one. So the people that were just kind of good at guessing got better. There were some other things that we did. I guess my number sense was a little bit better because I knew that if I divide by 2 there, and this would be the product of all the zeros. So that'd be -3 would be the product. So that would help me narrow it down to like 1 and 3, and I could choose between those, positive, -1, positive, -3. And I don't have to try maybe 1 or 2 of those before I find one that works. Okay. What you guys have is the graphic calculator in here, and that's where it really helps speed this process up. So the next thing you would do after you make your P over Q list is graph the polynomial. So I'm going to go to the graphing calculator, and I'm going to graph 2x to the third plus 11x squared minus 7x minus 6. Make sure I type that all in correctly. And then I hit graph. Make sure you don't have a stat plot on. It's going to screw up your graph. We see that polynomial graph there. It's odd degrees, so we know one end is going down, the other end is going up, and we see some changes in direction there. It's cubic, so we kind of get the general idea. We know what it looks like, but we see it crossing the x-axis here, there, and there. What number is this? We think it's -6. Let's trace -6 just to make sure. Yeah, it is, because we see the y equals 0 there. That's exactly what that point is. When you hit trace and type in the x value that you're trying, if you don't get 0 there, then that's not what it is. Okay, it's not a 0. It's not a solution to the polynomial. Okay, what number is this? It's -1/2. How do we know it's -1/2 and not maybe -3/5? Because those are really close together. We could trace -1/2. We hit trace and -1/2, and we're going to find that is correct. But why would -3/5 not even be a possibility? Wasn't on our P over Q list. That's how we know that. So the P over Q list is really helpful when we find ones that don't cross on a nice number. That it's hard to eyeball the difference in 2/3 and 3/5 or 1/2 and 3/5. They're real close on the graph there. What's this number? 1. Okay, so we got some options for synthetic division here to get the ball rolling. I'm going to use the easiest option, which would be what number? 1. It's an easier, because you're you've got to do a lot of multiplication for synthetic, right? So make it easier on yourself and use the 1. 2, 11, -7, -6. Okay, run that through. And we get excuse me, 2x² plus 13x plus 6 So we're factoring that polynomial. Because 1 is a 0, the factor that goes with the 0 of 1 is x minus 1. Okay, so it's taking what we did in 5.1 where they gave you the zeros and you had to build the factored form of it. You know, here's the 0 we found. There's the factor that goes with it. Now we've got a quadratic right here. Can we factor that without synthetic division? Yeah, we should be able to. 12 had to be multiplied to be 12, had to be 13. 12 and 1. So 2x squared plus 1x plus 12x plus 6. Multiply the 2 times 6, a times c. Factoring trinomial with the x method. Leading coefficient times the constant. And then group that. What's the GCF of that first group? X. That leaves us 2x plus 1. GCF of that group, 6. That should make sense that that's what's happening because we know this thing crossed the x-axis at nice places. So we got the x minus 1 factor that we already found with synthetic division. Then we have x plus 6 and 2x plus 1. We've got the factored form of that polynomial. But it took synthetic division to get it started.
Where did you get the 2x?
If I pull an x out of here, that leaves 2x and 1 in there. Pull a 6 out of that, that leaves 2x and 1. Just factoring a trinomial there. GCF is all that it takes to do the grouping. Okay. Now, once you get it in factored form, it would be easy to find all the zeros, right? Because you just set each factor equal to 0 and you solve it. And you got all the zeros of the polynomial. That's neat. How many solutions should this polynomial have? 3, because why? The degree was 3. Okay, so if the degree is 3, then we should have 3 solutions out of that. These are all what kind of solutions? Real or complex? Real, because they're all real numbers, right? They're all showing, and they all show up on the graph, right? They all showed up when we graphed that thing. It crossed the x-axis at all 3 of those places. 1, -6, and -1/2. It crossed there. All right. So the zeros, just to add to this, would be x equals 1, x equals -6, x equals -1/2. Again, that's coming from setting each factor equal to 0 and solving it. So get it in factored form. The zeros should be the easiest part. Getting it in factored form is going to maybe take a little bit more. All right, let's look at a bigger problem. Here's our function. X to the 5th minus x to the 4th minus 4x cubed plus 8x squared minus 32x plus 48. We want to factor and find all zeros. How many zeros does this polynomial have? 5, right? The degree is 5, so we should find 5 zeros. Does that mean that it will cross the x-axis 5 times? No. Not necessarily. Yeah, that's right. It could bounce off the x-axis if we have a repeating 0. If it's a complex 0, will it even cross the x-axis? No. Complex zeros don't cross the x-axis. So we're going to see what happens here. So the first thing that we should do to help narrow down the possibilities is what? P over Q. So we need the factors of 48 and the factors of 1. That makes this list easier because if the leading coefficient is 1, it's really just the factors of 48. So what are the factors of 48? 3, 4, 6, 8, 12. 3 times what is 48? 16. 2 times 24. And then 1 times 48. So we've narrowed that down. 1, 2, 3, 6, 9, 10, 20 numbers now. Okay, just getting the factors of 48. Now, what's the next thing that you would do? Graph it. So graph that polynomial. Y equals x to the 5th minus x to the 4th minus 4x to the 3rd 8x squared 32x. All right, some interesting things happening here. What do we see happening? Okay, so where does it touch the x-axis? What's that mean about positive 2? Has a multiplicity of 2 or 4. It's crossing here at what number? What number is that? Negative 3. So what's that mean about the multiplicity of negative 3? It could be 1, 3. Could it be 5? Yeah, because these other two, we know it's at least 2 on the one that bounces. So it could be 1 or 3 there. We don't know. But we do know that we do have a repeating 0 at 2. Right? And we have an odd multiplicity of 0 at negative 3. That's the big picture. That's what I want you to get there. All right, now, doesn't matter which one we start with. I'm going to go ahead and start with 2 and run it through with synthetic division. So if I pick 2 for my first one, I know that I can actually run synthetic division with 2 at least twice. So I'm going to run it through once and see what happens. So we run that through with synthetic division, drop the 1 down, that gets the pinball machine working there. Make sure I added it right. 24. Okay. So, zeros. 2. And now I know because of the graph that the multiplicity for 2 is at least happens twice. Okay, so I'm going to run synthetic one more time with the 2 because I know I can at least one more time. I don't know if it'll work a third or fourth time, but I know it will work one more time. So I'm just going to put my synthetic around that. If you want to rewrite it all completely, you can, but I'm not going to. Same process. Drop the 1 down. 2, that's 3, 6, 4. There we go. I'm not sure that 2 will work again. If I try it, we'll know. So I know 2 has got a multiplicity of 2. I'm just going to put a dot there so I know that, hey, I need to look at that again. If I try 2 again, this will decide if 2 counts 4 times or twice. Because if it counts 4 times, it's got to count 3 times first, right? So if I run that 2 through there, 1, that's 2, that's 5, 10, 14 times 2. That remainder is what? 40, right? Which is not 0. So what that tells us that the multiplicity is 2 for 2. Doesn't work. Now that means we need to go back to this line and do synthetic with what? -3. I'm going to back up. Put a -3 on the shelf. 1, 3, 4, and 12. There's a 0. There's -12. What do you know? The remainder is 0 there. Surprise, surprise. We saw that happening. We knew that was going to happen. So that gives us the 0, x equals -3. What do we have now? What is this? X squared plus 4. How can we solve that? Does it factor? If it was x squared minus 4, yeah, it factors really quickly and easily. But it doesn't, so subtract 4, get x squared equals -4, and then do what? Square root, right? Plus or minus on the side with a number. And what's the square root of -4? Yeah, plus or minus 2i. So what kind of solutions are those? Complex. Imaginary or complex? Well, complex would be what we're going to call them. This one is strictly imaginary because it doesn't have a real part to it. But those are zeros. So that means the multiplicity on the -3 was just 1. It only happened once. Because there was a negative underneath the square root. Anytime you take square root of a negative, the I is involved. Every time. All right. So we get x equals plus or minus 2i. So how many zeros do we have? We've got 1, 2, 3. Positive 2i is 4. Negative 2i is 5. So we have 5 zeros. Now, the instructions also said factor that thing. So we got to get a factor for each one of these zeros. So what's the factor for 2? X. Shouldn't it be x minus 2? Because it was positive 2. How many times does that occur? 2. So we got a squared on that. And then -3 was a 0. So what's the factor for -3? X plus 3. Now, the complex ones here, we're going to go back to what the quadratic they came from was, which is x squared plus 4. I don't guess it would be completely wrong to do this, but it's not very common to see that at all. Yes, sir. Yes, that's exactly right. It doesn't matter what order that you go in as far as your synthetic division. You pick whichever one you think is the best one to start with. I picked positive 2 because it's positive and I knew it repeated. If you started with -3, that actually the way on my paper there where I worked it out before, I started with -3 and worked it. It doesn't matter. I think what had happened when I made that copy of notes is the class said, hey, just start with -3 and go with that. And it works once, and if you try it again, it doesn't work. So then you move on to the next one that you know does work. That's the right thing.
How do you know whether to find the new proposals on B or find the
We did them the same way.
we did it through the division on here and then we factored it after the
Once you get to quadratic, we did the same way. Once we got to this quadratic, that's when we did our factoring. We got to this quadratic here, x squared plus 4. Once you get to a quadratic, then stop doing synthetic. Do synthetic until it becomes quadratic. And then you have either quadratic formula or factoring or solving by square roots like we did here to solve with. How do you know how many synthetic divisions you have to do? By your zeros. Okay? If there's a degree 5, How many times do I have to do synthetic division to get it to quadratic? Well, to get it to quadratic, quadratic has degree 2, right? So if I do synthetic once, twice, 3 times, that's 2 left. So you take your degree of the original problem minus 2, and that tells you how many times you should do synthetic division to get there. All right. Let's look at one last thing here. I know it's not much time left, but example F here. Degree 3 with zeros, 5 and 3 minus 2i. What do we know about this? This is something, again, that's reviewed from Algebra 2, but I just want to go through it one real quick problem. They tell us that this problem has degree 3, and then they give us 2 zeros. What zero did they not tell us about? Yeah, 3 plus 2i. Remember, complex and irrational zeros come in conjugate pairs. So if 3 minus 2i is a 0, then 3 plus 2i has to be a 0 too, by law. Okay. So then if we want to find the polynomial, we want to form a polynomial with those zeros. We start with x minus 5, x minus 3 plus 2i, x minus 3 minus 2i. Because that 3 is a positive in front, it's always a minus in front of it. And then you just alternate signs on your I part. Now we got to multiply it together. Not the easiest thing in the world here, but it's not too difficult. The thing is, do the stuff that has i's or square roots together, because then it'll get rid of that. So x times x is x squared minus 3x minus 2ix. So that's just distributing x to all 3 of those. And then I'm going to distribute negative 3. So that's another negative 3x. That's a positive 9. And then that's a positive 6i. Okay. And then I'm going to distribute 2i to all of those. So that's a 2ix and a negative 6i, and then a positive 4i squared. Which turns into what? Negative 4. That's right. This part right here, the I squared is equal to negative 1. So that becomes negative 4 is what that becomes. Just changes the sign. Now, looking at simplifying this part. X squared doesn't have any other x squared, so it comes down. Negative 3x and negative 3x, negative 6x. And then we have a negative 2ix and a positive 2ix. They cancel out. We have a positive 6i and a negative 6i. They cancel out. And now we're left with 9 and negative 4. Hold on. That should be a minus 4i squared right there. Because it's negative 2 and positive 2. So that makes it a plus 4. So that'd be plus 13 there. So we've taken the complex stuff and multiplied it together. When you do that, if you do it correctly, all of the i's will go away. Now all we got to do is multiply this together, which we've done before. So that's going to be x cubed minus 6x squared plus 13x minus 5x squared plus 30x minus 65. And final answer is x cubed minus 11x squared plus 43x minus 65. You can graph that final polynomial, and it should cross the x-axis at 5 and then not cross it anywhere else because of the complex stuff, okay? You want to start working over the weekend.
Cheyenne Ricci, report to the office.
You can. Page 357, which is 5-2, 11 through 32, 39 through 72. Okay.
Ms. Ross, you have a message in the office.
You guys have a good
Also,
weekend.
high school teachers did not turn on heat or air